Hi, everybody. Remember, at any point in time, just pause me so you can think through. I'm going to go through a few examples pretty quick, so just stop me if you don't want me to be a spoiler here. So looking at limits, remember it was the y value a graph was approaching. So this is, you got to picture the graph of y equals x squared. And as x goes to 3, what would this graph be approaching? Now you could use a calculator, or you could just say that, well, I know the actual value of that graph is 9 when x equals 3, and you've got yourself a limit. If you don't believe me, go ahead and get in your calculator and you'll see that right around where x equals 3, the y value is absolutely 9. That method of plugging it in is called direct substitution, and it always works until it doesn't. And I'll talk to you about what that looks like by the end of the lesson and then in the next video as well. So when we're looking at this graph, this is talking about the graph of y equals x, that line that goes up the diagonal. When x is 2, what y value is it going to? And the next one is picture the square root graph. When you're over there where x is 9, what does the y value look like it's doing? You can use your calculator, or you can kind of use your common sense. Well, I know the value when I take the square root of 9 is 3. That method is called direct substitution, that method of evaluating a limit. Okay, that being said, I think it's going to make it a little easier for me to talk, and you'll see me write this, right? Time is short, I'll do that. Okay, that should make it a little easier to understand these properties of limits that we're going to talk about right now. So you can pause if you need to write down some of the information that's up there. What they're saying is L, M, C, and K are all real numbers, and they're going to say the limit as we approach some C value for function f is L. It's a number they're not telling us. We're going to call it L. It could be 5, could be 100, I don't know. And then they're going to let the limit of G as that function, the y value, as we approach the same value of C, be a different number, maybe 2. Who knows? And if these are all true, then we can say some things. We can look at some properties. The first one's going to be the sum and difference rule. And this is the idea that if you have a limit of two functions added, you can totally break it up. You can find the limit of one and add it or subtract it from the limit of the other. And the answer would just be the limit of f as we approach C, which is L, times the limit of G as we approach C, which is M. That's the property. Holy cow. Let's just look at some realities here. Let's just give function f a name. It's going to be x cubed, okay? And function g will be x squared, and the arbitrary value of x is going to be 2. So we can see this like concretely. So if you don't know what the graph of x cubed plus x squared looks like, stop this, put it in your calculator, and then get really close to where x is 2 and see if you can use your trace button or whatever you want to find, a value button maybe, to find out what that limit is going to. I'm getting 12 in my good old calculator. What the property is saying is you don't have to do that. You could rewrite it and just say, well, what is x to the third going to at 2? And we know that that's 8. And add it to, well, what's the value of this parabola as x approaches 2? What's the limit? It looks like it's going to 4. And then you can add those together, and you're going to get the same thing either way. So if it's easier for you to split it up, please do so. That works for addition and subtraction. Holy cow, it also works for products. If you've got the limit of two things multiplied together as you approach a certain C value, you can split it up and to find the limit of the first one and then just times it by the limit of the second one. And what that looks like for us, I've written down here using the same arbitrary value of C we used in the example 1, and x cubed and x squared as my functions f and g. You have some options. You could go ahead and multiply them both together, or you could split them up. I'm going to split them up and use the property. And then times it by. And now I can work on these two little limits. This one goes to 8. And this one goes to 4. So I'm getting 32 as the limit. sorry, I should say we can just multiply the limit of one times the limit of the other. The other way you could have done it was you could have just gone with multiplying them together, sorry, and gotten x to the fifth. And you could have, if you knew that that graph approaches 32 when x equals 2. The x to the fifth graph goes to 32. Okay, I'm going to have to rip this out in folds of paper because I took up too much room there. Okay, just as there's a product rule, there's also a quotient rule. And it says that if you're finding the limit of two functions that are divided, you can find the limit of each one separately. So the limit of f over the limit of g. And of course, we will have the stipulation that m can't be 0. If you want to look at that in two case scenarios, I'm going to use our arbitrary value 2 and our two functions f and g that we've been using. And I can split this up into the limit of f of x, which is x cubed, and that limit is 8. And then the limit of our g, which was x squared, was 4, and you get 2. Or you could actually do it a different way and divide x cubed by x. And you could say, oh, what's the limit of the line y equals x as we approach 2? And you can get the same thing. My point is not to confuse you with this, but to get you to see there's a lot of different ways that you can manipulate these limits. When you go through your homework, I think you'll get solidified exactly what you can and you cannot do. All right, there's also a constant multiple rule. And that says if you're taking a limit and you've got a constant times your function, you can just take that k out of there, that constant, and do the calculus first. So this limit, I think it said was L, the limit of f of x, and then you can times it by k later. You can put that constant on hold. And I did come up with one of these here that you could use the property. If you had 5 times our function f, and we know this limit is 8, so you could take 5 times 8, we get 40. Or you could always just plug it in, or look at this graph. If you look at this graph in your calculator where x is 2, you're going to see that it's 40. And it's not a bad idea for you to get in those calculators. Start working on that stuff. Okay, and then the last rule that we have is the power rule. And that says if you're finding the limit of something to some kind of power, that you can actually find the limit first. Limits are really great. You can do all kinds of things. You can focus on the calculus first and just find the limit of your f of x. And when you're done, that's L, you can take that single number to a power. That's pretty cool. And if you want to see it, so-called in action here, I've used our f and taken it to the second power. And we said the limit of our f as we approach 2 was 8. And then we can square it later. Right? You could have also written it as taking the power of a power, simplified that function. And then you could have looked at this graph of x to the 6th and said, oh, right around 2, that's going to 64. And you'll get the same answer either way. All right, I have some also helpfuls. And the best way to understand the also helpfuls is to go ahead and try direct substitution. I told you it always works till it doesn't. If we plug in a 0 here, the sign at 0 is 0. And if I plug in a 0 for x, I'm getting 0 over 0. That's something called indeterminate. You are going to want to put this in your calculator and look close to 0 and see what that graph is going to. Spoiler alert, it's going to 1. And then the other one that you can look at in your calculator, I recommend you do that. This also at 0 gives you 1 minus 1. That's 0 over 0. That's indeterminate. You cannot determine a limit when something is indeterminate. 0 over 0 isn't 0, nor is it necessarily undefined. In this case, it was 1. So we want to make sure that we're looking at both of these. Keep this handy for your homework. And if you put this in your graphing calculator, as you look at x, as x approaches 0 of this funky graph, you'll see that that y value really looks like it's going to 0. All right, folks, I'll see you next time.